I think Monte Carlo simulations are very exciting, and we're going to learn all about them by throwing darts, by simulating the stock price movements, and by flipping coins. So let's just begin. So our first file named Monte Carlo A is just how we can use this to estimate the distribution of different probabilities given different events. In this case, the event is actually just rolling a fair die. So let's read a little bit about what is a Monte Carlo simulation first. Monte Carlo simulation is a method that uses random sampling to solve problems and understand certainty. The basic idea is that maybe you have a problem that is too difficult to solve directly, maybe to calculate the probabilities of that. Use random numbers to simulate many possible outcomes, then analyze the results to understand what's likely to happen. Think of it like this: instead of trying to predict the exact path of a single raindrop, we watch hundreds of raindrops and see the overall pattern they create. So here we are going to simulate a uh, fair dice. For a fair six-sided die, each number 1 to 6 should appear roughly the same number of times when rolled many times. This is a perfect example of Monte Carlo simulation. We can't predict exactly what the next roll will be, but we can simulate many rolls to see the overall pattern. The more rolls we do, the closer we get to the expected 16.67%, which is 1 in 6, right? But here's the thing. If we just do this random sampling, let's generate some random numbers, generated 10 random numbers. We can see that the distribution is very skewed. Like we see that the number 5 happened 3 times, which is 30% of the time, and number 1 only 10% of the time. If we run this again, now we get 20%, 20%, 10%. Let's run it one more time. Again, we get number 4 30% of the time. But if we increase the number of samples to like 1,000 and run it again, we see that the probability is actually getting closer to the expected probability of 16.67%, although there is still some variability, like this one is at 18. If we were to do this 10,000 times, then we should get much closer. This is also related to the law of large numbers, which we're going to take a look. Now it's much closer, as you can see. If we were to do 100,000 times. Now the thing is that in the case of a dice, we actually kind of know what the probability should be like. But in many circumstances, sometimes you don't. Like maybe with like stock price movements and stuff, we can simulate that too. Now, if we do it 1 million times, we should almost hit it on the head. Say 16.7, almost exactly as it should be. Okay, let's move on to our next example. By the way, the code files for this will be available at my Patreon. Link will be in the description or in the comment. Also, as a paying patron, you'll have access to over 500 large language model applications and exclusive videos. And I also offer consulting if you need help with your projects or just want to talk to me. Take a look at those memberships at my Patreon as well. So the next one is going to be trying to estimate pi, the number pi, by throwing darts. So this is an interesting one. If we just run this, we will see that we are going to draw a square, which is going to be our dartboard, and then we're going to draw a quarter circle inside of it, and then we're going to throw darts. So we first draw a square, which is a unit square, one by one, and then draw a quarter circle with radius 1 inside of it. Randomly throw darts and count how many how many lands inside or outside of the circle, and use this formula, which is pi over 4 is going to equal the total number of points that land inside divided by total points. Why pi over 4? Because this is a unit circle, so pi times r squared divided by 4, which is pi divided by 4 because r squared is 1. So pi over 4 is the area of this quarter circle. So now this is what it's going to look like. And then we are going to, after throwing 10 points, we see that, so here's a little visualization. We see that 9 of them goes inside the quarter circle and 1 of them outside. This means if we divide, our estimated pi is 3.6, but the actual pi is 3.14 and some change. So there's quite a difference, but we are already getting pretty close by just throwing 10 dice. So this is pretty fascinating, actually. Now, if you throw 50 of them, 39 of them land inside and 11 outside, and this gets us to 3.12, much closer. After 100 dart throws, we get to 3.28 versus 3.14. After 500, we get to 3.2 versus 3.14. After 1,000, we get to 3.18 versus 3.14. So, and we can see that with the final estimate, we could have, if you didn't know the number pi and just was estimating it using a Monte Carlo simulation, we would have said the pi is 3.18 or 19, and we would have gotten pretty close, accurate with an accuracy of 98.5. So here's the convergence demonstration. As you can see, with just 10 points, the error is higher. It didn't much improve in the 100 due to the random nature of it, but at 1,000, our error went down almost sixfold, and with 10,000, our error went down another tenfold. Yeah, the error decreases if you use more points. Now let's take a look at our next example, which is going to take a look at the law of large numbers. So this is why statistics matter in Monte Carlo, because Monte Carlo simulation relies on statistics to make sense of random results. The key concepts are sample mean, which is the average of the random samples that were generated. Variance, how spread out our results are, like how much some of the results vary from the mean or the average. The standard deviation is just the square root of variance, and law of large numbers mean why more samples means better estimates. So here's a sample mean demonstration. Let's roll a dice and see how our average sample mean behaves. So this is a fair six-sided die. The true mean is adding up all the numbers and dividing it by 6, so it's 3.5. I know you cannot roll 3.5, but that is the average, actually. So if you roll die multiple times, then if you average the value, if you roll 1 and then a 6, if you add them up, then it's 7 divided by 2 is 3.5, something like that. But if you roll it one time and we get 6, then the running average is 6. If you roll a second time and get a 2, that's 8 divided by 2, that's 4. If you roll another 6, then that's 8, and 6, 14 divided by 3, 4.6 something. And then as we go along, it varies. So that's where the variance comes in. Look, we started at 6, but dipped all the way down to 2.6. But as you keep rolling, we start approaching the true mean, which is true average, which is 3.5. So here, after 1,000 rolls, we get a sample mean of 3.522, and the true mean is actually 3.5. So variance and standard deviation. Variance measures how spread out our results are from the mean, meaning like how far away the actual result might be than the theoretical average. Like when you roll one die, you're hitting 6, but the average was 3.5, so you're like 2.5 times away, 2.5 points away from that. After rolling 10, then you're 0.7 away from 3.5. So that's like the variance in a way. And you calculate standard deviation is the square root of variance. High variance means results are way more spread out, unreliable. Low variance means results are clustered around the mean. Let's see this in action. If you flip this many coin flips, the average is going to be half, somewhere in the middle, right? So the outcomes are 1 and 0, but the average is going to be 0.5. But here, in this case, it turned out to be 0.490, and the variance is 0.499. So because the variance is the average movement to either side, and the standard deviation is the square root of it, which is 0.99. So of course, in a coin flip, the average is 0.5, and with each flip, you deviate half to left or half to right, right? Either to 0 or 1. So important note, for a fair coin, the variance, so you can read through this. The law of large numbers states that as the number of trials increase, the sample mean approaches to true mean. The mean means average. This is why Monte Carlo simulations become more accurate with more samples. Let's demonstrate this with dice rolls. So if you roll the dice 10 times, then sample mean is 4.4. That is zero point 0.9 away, then accuracy of 74%, because the actual mean is 3.5. With 50, our accuracy increases, and it increases to a maximum of, with 5,000 rolls, to 98.5. As you can see, because of the random nature of it, with actually 100 and 500 dice rolls, we actually gotten higher accuracy. The law of large numbers states that if you were to keep rolling higher and higher, then your accuracy is going to improve. As we have seen in the first example, if you roll it 5 million times, then you're going to get very close. So Monte Carlo reliability, let's estimate pi multiple times with different sample sizes to see how reliability improves. So again, the same thing here. More samples mean smaller errors. Statistical confidence. Uh, statistical confidence means tells us how sure we are about our results, meaning if we estimate pi to be 3.14 with give or take plus or minus 0.01, this actually translates to 95% confidence that the true value of pi lies between these two variations. So this is a statistical concept. These are statistical concepts. So statistics actually is pretty exciting. I'm studying it currently, and some of this stuff comes up as well as it comes up in Monte Carlo, because statistics is the methods by which you interpret the results. So let's move on to something exciting, which is stock market simulation. The Wall Street uses this all the time, or you may hear on the news that maybe some hedge fund or somebody who's an expert on the stock market may say something like, "We have simulated the stock 1,000 times or 1 million times, and we expect the movement to be this way or that way." That is usually done with Monte Carlo simulations. So this is called random walks in finance. Let's see how this is done, give or take. Very simple example of it. Stock prices don't follow predictable patterns, but they do follow certain statistical properties. The random walk model captures this. For example, each day the stock price can go up or down by a random amount. The probability of going up versus down might be slightly biased. The size of the daily change follows a normal distribution. Over time, this creates a realistic stock price path. Right? I mean, imagine like a company that sells sunscreen lotion or something like that, and maybe they start selling more in the summertime, so their stock goes up in the summertime, right? So this is so different. You can assign probabilities to certain biases and actually include that in the Monte Carlo simulation. But if you just do a completely random walk, meaning if you just run a stock price simulation for 30 days starting at $100, and each day the price may move 100 $1 up or down, each one of them be having a chance of 50-50, then that is random walk. And in day one, it goes up by $1. And at the end of day 30, it ends up being at $98, uh, $2 negative. And if you do this for 30 days, we can do this. Here's a chart for it. Then the high and lows are situated here. But the geometric Brownian motion is a more realistic stock price model where you kind of try to introduce some reasonable biases, right? First of all, it includes percentage changes, not absolute dollar amounts, volatility, how much prices swing daily. These are all like estimates, right? Stock prices don't move 90% in a day. They may move 2-3%. Different stock tickers will have different volatility indexes and things like that. Drift, the long-term upward trend, because the stock market has been on an uptrend, obviously. So you include those types of variables and then run a Monte Carlo simulation. Also, the multiplicative nature, because it compounds. So there's a formula for it. The left side is change in the stock price, final versus the initial, the current stock price, the percentage change. Drift term, expected annual return. So this is an assumption, right? And then time period, for example, for one trading day, out of all available trading days, this pushes the prices upward over time because you expect 8% annual return divided by this, then it gives you what you expect daily upward drift. Volatility, annual volatility, you calculate this or, doing some statistics and then square root of time, random shock from normal distribution. So these are some more advanced values that I don't pretend to understand 100%, but it would be interesting to get into. So then all this is to generate a more realistic simulation. Why this works? Because prices change by percentages. The time scaling prevents unrealistic volatility. Normal distribution Z creates natural price movements. Drift creates long-term upward trend. Volatility creates realistic market swings. Okay. So here's also the exact calculations. You can look at the file if you download it from my Patreon or pause the video and read it here. But the key insight is that the drift term provides consistent upward pressure. Volatility. Let's take a look at the chart. See, it fluctuated, but ended up being up in the end. Volatility term creates realistic market fluctuations. Time scaling prevents extreme volatility over long periods. Normal distribution creates natural price movements. Formula works with percentages. All right. So here's for 30 days. This particular simulation provided 3.6% return. But better yet, with Monte Carlo simulation, we can run the same simulation for 30 days or for a whole year, like 1,000 times, and we can average the results. So this is what what they're referring to if you hear it on the news or read it on an article. Because if you think your assumptions about a stock price is accurate, such as your expected return, volatility, then you almost simulated, well, what would happen from today to a year from now if this were to happen like 1,000 times. So when we do it this way, we find the mean final price across all simulations is 115, so that's about 15% up. Median price is 111, that is the price right in the middle of the distribution. Minimum price is 37, so it actually it went from $100 to $37. Sometimes that is the minimum that it found itself in. Maximum price, sometimes it went up over 300%, and the standard deviation from the mean was about 38%, meaning you can expect 115 as your baseline, but expect 38%, $38 movement on either side within 1 year, given the simulation. Probability analysis is that that 90th top, like 90th percentile means the most likely scenario, I believe. No, 50th percentile means actually, this means that 10% of the values are at or below $72 in this distribution. And this, when you run it 1,000 times, you get 1,000 different values, right, for the ending price. 25% of the values are less than is equal to or less than 87. Half of the values are 111. 75% actually is 136, and 90% of them are 165 or below. So probability of loss is 37%. Probability of doubling is 3.9%. Expected annual return is 15%. That's remarkable if you can catch a, like that. Example price paths, for example, here are five example price paths over 1 year. Path 1 starts at 100. In the middle, it's 135. At the end, it's 177. Let me run this again, actually, because the terminal gets broken sometimes. Here. Yeah. So this is, for example, path 1 is starts at 100. I think this is a mistake. Yeah, here. It starts, so path 1, I mean, but let's just take a look at the numbers. It starts at 100 and ends at 93. In the middle, it was like 103. So this example ended up actually losing money. Price scale there in the path 2, it again ended with a loss, but in path 3, it made money, and the path 4, it lost, and path 5, it actually increased quite a lot. So you can see that the simulation can vary wildly, just as like the stock market. So the techniques you've learned from the foundation of stock price simulations, options pricing, portfolio risk analysis, are very simply, right? simulate mini stock price path to expiration, calculate payoff for each path, average payoffs, discounts. Yeah, so this is how Wall Street uses Monte Carlo every day. Yeah, so these are interesting. You can build on these and explore them yourself at Cursor or however you like. There's a this README is empty. I don't think it is really needed. Requirements are pretty simple. So this is it. And like I said, these will be available at my Patreon. Uh, do consider subscribing and becoming a member, as that helps me immensely continue making these videos. And also, you will have access to over 500 interesting projects along with exclusive videos. And like I said, I also offer consulting. If you need help with your projects, consider that by taking a look at the option at the Patreon memberships. Thank you.